Hello, everyone. I want to talk about section 9.3, stoichiometry of gaseous substances, mixtures, and reactions. The learning objectives here use the ideal gas law to compute gas densities and molar masses, perform stoichiometric calculations involving gaseous substances, and then I'm just going to say it this way, you use the law of partial pressure in calculations involving gaseous mixtures. Again, I'm not caring if you know the names of all of the people who were involved in these processes. So there's kind of a lot in this section. However, it is somewhat review in that these are all mostly ideas, I should say. There's a few new things here, but these are mostly ideas you've already seen before, and it's a matter of taking some of these big ideas and combining them together into even bigger ideas. So just be aware of that. We're not going to get into too much detail on doing specific examples here. I might be sharing additional resources for those in a separate post. So there's kind of a lot here. We're just going to do a little bit of a drive-by. It does not mean it's unimportant. It's that these are things you already know, and it's a matter of combining them together. So this first thing we'll see is gas density and molar mass. All we're basically doing here is taking the definition, the ideal gas law, which we're showing here, and the definition of density, and then combining them together. So we're showing that here, and then we're using this symbol as the molar mass. The molar mass is a ratio of mass per moles. So when you are combining these ideas, when you combine the ideal gas law and the density, you would also need to know the molar mass. So your book is going through a derivation of kind of these ideas, and it's saying, okay, density is equal to molar mass times pressure divided by R divided by T. If it's helpful for you to memorize that equation, that is fine. However, you could also just figure it out when you need it, because you know this equation and you know this equation and you know this equation. I mean, we haven't defined it as an equation before, but you know what that relationship is. So you can combine those ideas together to come up with this if you need to. There's an example here, so you might want to look at that as an example of measuring gas density. You'll notice it's basically a function of pressure, temperature, and the molar mass. So when we have our tables where we say, okay, this is the density of, say, iron, or the density of a piece of wood, for a gas, it depends on the temperature and the pressure, right? So we can't say, okay, this is always the density of a gas, because it will change with temperature and pressure, much more so than any solid would. The solids will change a little bit. We'll talk about that in a later module, but they're close enough that we can have reference values to look at. We don't have those for gases. We would need to use an equation such as this. We can also frame the same equation in a way to look for the molar mass. So here we're using the ideal gas law, and I'm not sure why it's using the word molarity here. This is the molar mass, right? Moles, mass per mole. So the little case m is mass, the little case n is mole. So mass per mole. So not molarity, but molar mass. And if we combine those equations, we would get molar mass is equal to mass times R times T divided by P divided by V. Again, this is something you can do. You can algebraically do it yourself to come up with that equation if you needed to. I'm just going to say this next example is going a little bit deep in terms of going way back to Module 3 material, potentially you could have a homework question like this. However, this is more detailed than would be on a quiz or exam. But you can look at that to kind of see how that works out. So the idea we just looked at is basically this part right here, and we're going back, we're combining ideas from previously to get the molecular formula. This next one we will actually be doing in lab. So that's where we'll get some practice with this idea. Okay, the next thing we'll talk about here is the pressure of a mixture of gases. Again, I don't care that you remember the name of this law. And this one is often sometimes initially confusing to people who see it the first time, because this looks very complicated with all of the the summations going on here. But the basic idea, and this is probably so obvious you don't often realize that it's a big deal to even say it. When you have a mixture of gases, if they're ideal gases, we can simply add all of their pressures together to get the total pressure. So we're showing here a mixture of gases, add those together to get the total pressure. That's it. That's what we do for partial pressure. So the idea of partial pressure is that in a mixture of gases, a particular gas has a certain pressure. This is something that could be important related to additional things that we might have to calculate, as we'll see here in a moment. Another way we could frame this is with the idea of a mole fraction. Mole fraction is, instead of talking about the pressure, we talk about, well, how many moles do we have? So the mole fraction is then directly related to the partial pressure. So mole fraction is moles of one component divided by the total number of moles. And then we can say that the partial pressure of one component is equal to its mole fraction times the total pressure. So that relationship is there. Again, some of these are sometimes so obvious that you would wonder why we need a law for them. But it turns out there is a reason for that. We won't quite get to it in this class, but we can hint at it in a later section. So some examples here of using this idea. So these could all be relevant examples. Here as well. Okay, so now I want to talk about an example of why this idea matters of the partial pressure, and that's a collection of gases over water. And this is when we do an experiment in the lab. This is the means we have for finding out how much of a gas we have. So it's actually very relevant in terms of experimentation. So how this works is you have a reaction that is creating a gas. That gas is then basically bubbled through some water and then collected in a flask over the water. So that's a way of collecting the gas such that we can easily determine its volume and its pressure relative to atmospheric pressure. Now the challenge here is that when we do that, the gas we are collecting is not just the gas we made, but there's also some water vapor there because we're bubbling it through the water. So when we do that, what we have to do is we have to account for that. There's a vapor pressure of water that would be present there. And it's a function of temperature, and we're showing that relationship here. You don't have to worry about this part of it too much right now. This is something we might revisit in a later chapter, so don't worry about the graph. But the idea is we can look this up on a table, and we can say, okay, we're at 20 degrees Celsius, and the vapor pressure of water would be this amount. So of the gas that you have in that container, this much of it, in terms of partial pressure, is from water, and we would have to subtract that out of your results. Okay, so this is an idea that you want to be aware of as well. So there's an example here of using that. And then finally, for this kind of section on applying the ideal gas law, is the idea of chemical stoichiometry. And so the basic idea here, again, there are no, so the new concepts we have for this section were basically the law of partial pressure, which was, hopefully pretty obvious, and then maybe applying that when we maybe didn't think about the water vapor having a partial pressure we needed to account for. This part, however, is not new, right? We know about stoichiometry, we know about gases. The new part is combining those two ideas. So when we talk about moles, we've talked about moles in chemical reactions, and we've also talked about moles in gases. Those are the same ideas, and we can link them together if we need to. When we have a chemical reaction and we solve for moles, those moles can be used then in the ideal gas law. Likewise, when we have the ideal gas law and solve for moles, those moles could potentially be used in the stoichiometry question. So that's kind of the idea here, is that the mole concept is now linking gases to everything else we talked about being linked with the mole concept earlier. So that's, again, showing how important that idea is. Here is an example. I think this is a great example to look at in terms of reactions of gases. So you have, I'm going to walk through this a little bit with you, and then there'll be further examples that you can look on in Canvas. So this is a gas phase reaction, and what we're doing here is we have 1 volume of this gas and 5 volumes of this gas based on the number of moles. So that much. And over here we have 3 volumes plus 4 volumes of the products. And we're saying that the propane completely reacts, so that will be all the way gone. And we're looking for the volume of oxygen at those temperatures necessary to react with the volume of propane that is provided there. So what we can do is we can say the amount of the propane is equal to 5 times the amount of oxygen. Okay, so it's a 1 to 5. Now we're saying volumes here, so we're saying liters, and you might be a little bit worried because we weren't really allowed to do this earlier. If we had a mass, we couldn't say mass to mass. But what we're doing here is we're saying, okay, when we do this, we know that for every amount we have of one thing, we have this ratio. And we also know from the law of partial pressure, so let's go up and look at that again. From this one, we know that we're basically directly relating moles and volume. That's what this is saying. Okay, we're directly relating moles and volume. They're not different based on what they are, right? So we're not using molar masses here. For every mole, you have a certain volume. There's a ratio there, and that ratio would be the same for every gas in that mixture. So because we are here looking at a mixture of gases, let me go back and find the example we're looking at. We can do that. We can get away with this in this case because there's that relationship. We could go through a step of, okay, well, let's figure out how many moles we have, do our conversion, and convert back to moles. Whatever that conversion would be, it would be exactly the same thing. So we would be converting from liters to moles. We'd be dividing by something, and then on the other side we'd be multiplying by the same thing. So that's kind of why we can get away with this little shortcut here. And then kind of a similar thing here, although we're using different units here, so billions of cubic feet, but getting at the same thing. And then this one, example 9.19, is where we have to go back to what I was saying, where we do have to combine those two ideas together. So we're given some conditions in terms of temperature and pressure. We're given an amount of something, and we want to find the amount of hydrogen. So a few things to point out as you're doing this. First of all, when you use the ideal gas law, we're showing, some temperature, pressure here. We know we're probably using the ideal gas law. You can only use that for a gas, okay? So we look at the equation. What is the gas? The gas is only hydrogen. And the question is also saying volume of hydrogen, so that could be a clue as well. But you can only use this information for the gas, hydrogen in this case. And then for the other part, we do mole, stoichiometry like we've done earlier. And then we bring those two ideas together. So the answer to the stoichiometry goes into our use of the ideal gas law. Okay, so that's that idea of bringing those two things together. So pretty involved. You'll want to go through and do some examples of this, of how to do that kind of a calculation. So that is it for this section. Please look at some examples before moving on to the next section.